Welcome back to session 18 on plane stresses, and we're in portion 2. In this section, or in this portion of our session, we're going to discuss what are in-plane max shear stresses. And again, this sounds like a bunch of jargon, and each one of these terms has significance. Okay, we're talking again about planar stresses, and we're talking about shear stresses, and we're talking about the maximum shear stresses, okay, associated with an orientation of element in that plane. Okay, so what are we talking about, or what is a state, or what is a depiction or orientation associated with having a maximum in-plane shear stress? Well, what are we going to do? We're going to start with an element. Okay, we're given some sigma x, sigma y, sigma tau xy, and we're going to rotate to create an orientation or a state that shows a maximum shear stress. And this is associated with normal stresses going to some value that is not necessarily 0. Turns out they go to kind of this average value. Okay, so it's like sigma x plus sigma y divided by 2. Okay, but we're looking for a state with maximum shear stress. And foreshadowing in the last portion, we'll talk about how, okay, well, we're looking for maximum, right? So that means that we are going to want to take a derivative and set it equal to 0. So here, what we need to do is find an orientation, okay, that we have maximum shear stress. And if we've plotted out the whole state of shear stress, okay, as a function of angle, which we've been doing, right, we can kind of look at the graph, right, and be able to pick out where do we have maximum in-plane shear stress. So what we end up suggesting is that we can find an orientation that goes from this general state of 2D stress on a plane to one in which we have maximum shear stress and we are still having some type of, potentially or not potentially, still some normal stress. Okay, so the normal stresses, there is a case of pure shear, okay, where they can go to 0, but typically, in most cases, what you'll see is that they reach an average value and that they end up being the same. Okay. But we'll go over some different scenarios. So here we have an orientation that we could call rotated by theta s, and we might say, okay, we've rotated theta s1 here to get our maximum shear stress, and we can also rotate 90 degrees from that, right, so that we get a shear stress that we consider still maximum. It actually becomes like, it could become a minimum, right, because now we rotate 90 degrees and we go from like maybe a positive tau max to a minus tau max, right, so a minimum. Again, it's not always super important to know, okay, this is the the theta s1 orientation and theta s2 orientation. What we need to realize is that they're 90 degrees from each other, and that they both correspond to a state of maximum in-plane shear stress. So let's do an example. We have an element with sigma x equals 50 megapascals, sigma y equals 100 megapascals, tau xy equals 10 megapascals, and we're asking what is the maximum in-plane shear stress and what is the associated angle of rotation theta s, or what could be associated angles. All right. So once again, we've got our element here, and then we're getting to some rotated state of stress where we have a theta s and we have maximum shear stress. And once again, I recommend you go to Colab and you look at example 18.3, and 18.3 will spit out these plots. Okay, so we have sigma x prime, sigma y prime. Well, where is the shear stress tau x prime y prime, where's the shear stress tau reaching a maximum? Okay, well, this is a good selection right here. Okay, we can kind of see it's at a peak, and we look, okay, the minus of that is over here. Okay, and we can take a look at when we have an equivalent average, okay, for being kind of right smack in the middle, all right, of the top and the bottom. That, I guess, is the average of 2 points or 2 values in the sigma x prime and sigma y prime. And it's actually the average value at any orientation. So, if I'm at this orientation, I take this sigma x prime and this sigma y prime, right, and I average them. I hope that I can get a sigma average that's equal to this, all right? But I can get it just from the sigma x and the sigma y. This will become more clear I think in the last portion we covered today. But this horizontal line corresponds to the average of sigma x and sigma y. And it also ends up being the average of any pair of sigma x and sigma y prime, sigma x prime and sigma y prime, as we rotate the element. So we can write that over here as well. They end up being the same. And we say, okay, where do we cross these lines? Or where do we cross the sigma average lines, right? And then, well, right here. And we can say those also correspond to a sigma S1 and a sigma S2. Right? So now we've got maximum shear stresses, minimum shear stresses. We've got corresponding normal stresses. We can run the code in example 18.3, and we see that we have a maximum shear stress of 27 megapascals and a minimum of minus 27 pascals. Okay, and we see that there are sigma x prime and y prime that are the same. Okay, at this corresponding with this maximum shear stress or this minimum shear stress at specified angles that we've calculated out as well. Okay, again, this is finding points. There's 1,000 points sampled, okay, on these curves, and then I'm saying, okay, find the ones that are like, closest or the minimum or the maximum, all right, for the shear stresses. And when we're doing principal stresses, we were thinking about the maximum sigma x prime and the minimum sigma x prime, the maximum sigma y prime, and the minimum sigma y prime. Now we're talking about the shear stresses, looking at the max shear stress and the min shear stress. So if we are associated with theta S1 or one of the ones that we like, okay, we look at the maximum shear stress and we say, okay, that was at 34.1 degrees, and the average normal stresses, average of the normal stresses, is 75 megapascals. All right, at any orientation, the average is that, but this is where they're the same and they equal that average. If we go to 124.1 degrees, we find a minimum shear stress at minus 27 megapascals, and then we again have the same average normal stress at this location. Okay, so that's pretty much it. We've figured out, okay, what's the maximum in-plane shear stress, which also is corresponding to a minimum in-plane shear stress, right? We've calculated that out, and we also know what the orientation is there. And for kind of a bonus, we've also figured out what the normal stress is for this element at that orientation. Now, let's just talk a little bit about the relationships between theta p and theta s, right? So these are the orientations associated with the principal in-plane principal stresses and orientations associated with the maximum shear stress, theta s. And if we just look at some of the data that we've been plotting for sigma x prime, sigma y prime, and tau x prime y prime, we can kind of look and find the mins and the maxes, or we can start off by looking at, okay, where is the shear stress equal to 0? So mins and maxes in the normal stresses correspond to shear stress being equal to 0. Okay, so let's just draw that line, all right, like we've done here, and we'll say, all right, we have a theta P1 right here, where this is going to be a max. We have another value, okay, where we have, oh, this is backwards, guys. Oh, okay, well, this is why we do what we do. This is not theta P1, that's theta S1, right? Because that's where we have a maximum shear stress. This one we would consider to be maybe theta P1, all right, where it's crossing through 0, right? So we have corresponding maximum normal stresses. This one right here is going to be not theta P2, but would be theta S2 because we've got a minimum shear stress down here. And then this one over here, okay, this one is going to be not a theta S2, but a theta P2. My mistake. All right. So if we look, though, at the spacing of these values, what do we see? We see that they're 45 degrees apart. And we can do that if we go around, we circle back around, okay, we would see that, yeah, so you could also say there's a phase of 45 degrees between this theta P2 and this theta S1. And this is very interesting, right? That yeah, actually you have to be kind of careful what I said there, right? Because you're actually going, yeah, you go beyond, because it's actually, you can go 360 degrees, right? So you could describe even more of these if you want at their 180 degree increments from what you have here. But anyway, yes, these are 45 degrees apart from each other. And that's important to realize, okay, that if you find the state of principal stress, right, you can go 45 degrees either direction, and then you're in the state of maximum shear stress for a planar element, right? And just like in the last session or the last portion, we said, why do we care about the principal stresses? We care, right? What did we say? We said that it's because brittle materials fail with normal stresses, okay? In this case, we're looking at maximum, or in this portion, we focus more on looking at maximum shear stresses. Turns out the ductile materials fail more frequently in shear. Okay, so we're beginning to kind of be able to take a combined loading, right, the stress at a given orientation, and say, hey, what are the maximum shear stresses that you have here? And if that's the mode of failure, and that's what's really going to cause this ductile material to fail, how much, what's the quantity? What are the quantities of these values? Okay, and then how can I calculate them? Right, and so that's kind of the point of what we're doing here, to be able to kind of understand, get a mental picture that something might have a combined state of stress, but if I can simplify it into shear and normal components that are most relevant, then I can predict whether failure will be happening. Okay, so like we just said, yes, there's a 45 degree offset between the theta P and theta S, or in other words, between the in-plane principal stresses and in-plane maximum shear stresses. So here are some additional details, okay, kind of repeating the same thing. That is, if you have maximum shear and you rotate by 45 degrees, you can have maximum normal, right, or principal stresses, okay? And there's kind of a pretty um, famous example, all right, where we can have just in plane max shear and only shear stresses. Okay, so there are no normal stresses here, and that's in what's called pure shear. Okay, so this is a case of pure shear, like we see there, and this element, for example, on a shaft, is being twisted. There are no normal stresses coming through this element or through this shaft, cylindrical shaft. There's just torque being applied at either end. And we've kind of looked at these cases of pure shear previously. And what's interesting is that you can then also find 45 degrees. If we rotate this element 45 degrees, we can find a state of maximum or normal principal, or max, or just in plane principal shear, in plane principal stresses. They're normal stresses. Okay, and this calculation can be done without too much difficulty. And in reality, okay, they're both drawn in the same direction here, but what you'll find is that one of these, like if this is sigma 1, right, then this would be sigma 2, and we'll see that in pure shear that sigma 1 is actually equal to minus sigma 2. Okay, at least the way these are drawn. So you'll have tensile normal stress on one side, and we'll have compressive normal stress on the other side. Here's question 2. If we have an element with sigma x equals 100 megapascals, sigma y equals a negative 100 megapascals, tau xy equals 0 megapascals, what is the maximum in-plane shear stress, and what is the associated angle of rotation theta s? Okay, and hint, hint, we just talked about a situation where you have sigma 1 equals to minus sigma 2, and there's no shear stress. Okay, so this is a case we have pure shear. Okay, and so figure out what the associated tau xy is in this case. And you can use the scripts to help you with that. And then after you do that, you'll be like, oh, okay, maybe that was obvious. And it will become more obvious when we discuss more circle how to approach this type of problem without having to use all these equations. All right, thank you. This is the end of our second portion.